Have you ever really stopped to think about how something like your smartphone or a massive supercomputer actually works? How is that incredible dance of electricity managed inside? Well, it turns out the answer lies in a couple of laws from way back in the 19th century, and believe me, they are the bedrock of pretty much all modern electronics. Let's dive in.
Okay, so take a look at this. This is a modern computer chip. We're talking about billions, with a B, of tiny components, all woven together on a surface that's about the size of your fingernail. I mean, the sheer density of it, it's just absolutely mind-boggling when you think about it. So, that crazy complexity, it brings up a huge question, right? How on earth do engineers manage to control the flow of electricity in something so packed, so incredibly dense? How do you make sure that every single one of those billions of parts gets exactly the right electrical signal it needs to do its job? It seems impossible.
While the solution, and this is the really amazing part, comes from way back in the 19th century, a physicist named Gustav Kirchhoff came up with two, you could say, elegantly simple laws. And these two laws give us a perfect, systematic way to figure out what's happening in any electrical circuit, no matter how ridiculously complex it gets.
All right, so let's start with the first one. It's called the junction rule, but you'll usually hear it called Kirchhoff's current law, or just KCL for short. And this one is all about what happens to electrical current when paths cross inside a circuit.
So, the core idea of KCL is really all about balance. It's super simple. The total amount of current flowing into a junction has to be exactly the same as the total amount of current flowing out of it. It's basically the law of conservation of charge in action. You can't just lose electricity, right? It doesn't just disappear into thin air.
And here you can see what we mean by a junction or a node. It's just any spot where a bunch of different circuit paths meet up. Honestly, the best way to think about it is like plumbing. Imagine a bunch of water pipes meeting at a single joint. The amount of water flowing in has to equal the amount flowing out, right? Well, it's the exact same idea for electrical current.
And applying this law is actually a pretty straightforward four-step process. First, you find a junction. Then you just assign a plus sign to any current going in and a minus sign to any current going out. You add them all up and voila, the grand total has to be zero, every single time. It's how engineers know for sure that the flow of charge is perfectly balanced.
Okay, so KCL is all about the conservation of charge. But Kirchhoff's second law, that one tackles a different, but just as important fundamental principle, the conservation of energy. And really, understanding this difference is the key to seeing just how powerful these two laws are when you put them together.
And that brings us to his second big idea, the loop rule. You'll also know this one as Kirchhoff's voltage law, or KVL. So if KCL was about what happens at a single point, a junction, KVL is all about what happens when you follow a complete, closed loop in a circuit.
KVL is really all about energy balance. Think of it this way. In any closed loop, all the voltage you get from your power sources, like a battery, has to be completely used up by all the components in that loop, like resistors. I love the journey analogy for this. Imagine you start a hike with a certain amount of energy. By the time you get back to your starting point, you've used all that energy up. Same idea.
This little circuit here is a perfect example of KVL in action. See that voltage source, V sub S? That's our starting point, our energy supply. As the current goes around the loop, each of those resistors uses up a bit of that energy, which we call voltage drop. And what KVL tells us and guarantees is that if you add up all those individual drops, V1, V2, and so on, it will always equal the voltage you started with from the source.
Okay, so now we've got these two powerful laws, KCL and KVL. The big question is, so what? How do we take these sort of abstract ideas and use them to understand what's actually happening with the real physical parts of a circuit?
Well, this is where it all comes together. When you combine Kirchhoff's laws with another famous one, Ohm's law, you get a powerful toolkit. Engineers can then predict exactly how passive components, the ones that don't create energy themselves, are going to behave. We're talking about resistors, which slow down current, and then inductors and capacitors, which are all about storing energy. These laws are basically the mathematical language we use to describe what they do.
And once you can model those basic building blocks, you can start putting them together to build, well, anything. This is the moment where that fundamental theory gets put into practice to create the insanely complex technologies that run our world, like microchips.
So check this out. On the left, you've got the physical reality of a microchip, all that crazy intricate wiring. And on the right, that's the software model that engineers use to design the thing in the first place. And that software, it's built entirely on the principles we've just been talking about. This kind of software, a famous example is called SPICE, is basically a digital sandbox for designing microchips. It uses KCl and KVL to build a massive system of equations that models every single one of those billions of components. This lets engineers test everything out virtually before a single physical chip is ever made. I mean, can you imagine the time and money that saves?
There's this great quote that really says it all. Circuit theory is one of the most successful and often used theories in electrical engineering. Its success is mainly due to its simplicity. And that's just it, isn't it? The genius of Kirchhoff's laws is that they are so simple, so elegant, that you can apply them on a scale that is just almost impossible to wrap your head around. So if there's one thing to take away from all this, it's that a couple of fundamental physics principles figured out over 150 years ago are still absolutely essential for creating the technology that defines the 21st century. It's pretty amazing.
But, this all leads to one last really fascinating question. We keep making components smaller and smaller, pushing right down to the scale of individual atoms. So at what point do these classical laws of physics start to, bend, or even break? And what new rules are we going to need to figure out to build the next generation of technology?